Hi, I'm Professor Angela Rasmussen from the Electrical and Computer Engineering Department at the University of Utah. Today I wanted to go over a technique called the straight line approximation. And in the past you've seen us be able to find each point on a magnitude graph and do that for various values of omega and then connect all those to create a continuous graph. We did that for both magnitude and phase. So now we want to look at an equation and say, can we actually just approximate these by hand and create those Bode graph plots? And this is what this technique is going to teach us. So this is also called a hand approximation. So the steps to do this, I have outlined in the notes the procedural steps to drawing this straight line approximation. So first is to get it in what is called the standard form. So after you analyze the circuit, and remember you want to analyze it with the S instead of j omega, so that you get an equation in the form of S. Again, S was that S-plane instead of looking at more of the Cartesian vectors or the phasor vectors that we looked at previously. So the S-plane is what we want to first get the form in. So we use the S, and then we're going to have a whole bunch of number coefficients out in the front of the equation, and then each term in here we want to have it be a +1. So you want to make sure that you get all of the values in that quantity to be S over some number +1. And we call the top ones on here the zeros, and the bottom ones we call poles. So next we want to determine the values of what these zeros and poles are. So the values of them is going to be this number that is underneath the S. So each of those two are considered our zeros, and this P1 and this P2 are considered our poles. So note that if there is more than one polar zero at the same frequency, then we just multiply its effect, and you're going to see what the effects are in a second. So the first step is what we want to draw the magnitude plot. So the magnitude plot is going to have different cases. So you have to look at the equation itself and say, which case do I have? So the first case is that you have no poles or zero at the origin. All you're going to do is take 20 log of all of those numbers that were out in front. So that was these numbers here, this K, Z1, Z2, P1, and P2. So if there's any other numbers out there, you're going to take those numbers and then just take 20 log of that. That is going to give you what we call our starting values on the magnitude plot. It's going to stay at that value until you get to what is called your first break frequency. Those are determined by the values you found for your zeros and your poles. The other case, so this is a totally separate case, is when you have a polar zero at the origin. If that is the case, the equation when you take the magnitude actually starts out with a starting slope. So you have to figure out where does that intersect in your graph. So we need to find that one point, and then depending on if it's a polar zero, we know the slope of that line. So we're going to pick a frequency less than the lowest polar zero value. Then we're going to plug in the frequency and just calculate that one frequency. So we don't have to calculate all of them, but we do have to calculate the one. So you take the magnitude of the equation, plug in omega at that value, and that will give you the one value. If it is a zero, then you're going to have a plus 20 dB slope going through that point. If it's a pole, you're going to have a negative 20 dB per decade slope going through that location. You're going to start at either of the starting points. You're going to start with the slope. It's going to be 0 if it was the first case. It's going to be a slope if it's the second case, either a plus 20 dB per decade or a minus 20 dB per decade. And then you're going to have it continue along that till it reaches another polar frequency. Once it reaches the pole or zero, if it is a 0, you're going to add an additional 20 dB per decade. And if it's a pole, you're going to add a negative 20 dB per decade. So note that for this, you add this change. So keep adding on the changes, as that is the way the magnitude works. For a phase, it's a little bit different. So to do the phase plot, the polar zero actually has an effect 1 decade before that frequency and 1 decade after. For the magnitude, its effect happens right at that frequency. So for example, once you reach that frequency, it either changes by 20 dB up or down in the slope value itself for magnitude. Phase is totally different, so make sure you don't confuse that you have to use different techniques for both of them. So for the phase plot, again, you have the two cases, a case when you have a polar zero at the origin and when you don't. So if there's no polar zero at the origin, if you don't have a negative, meaning that the constant is a positive value, then your phase, starting phase, is going to be 0. If you have a negative, then your starting value is a plus or minus 180. That just means that it's negative. So instead of, if you think about the imaginary and real plane, it means that you are in a negative value, and it's a negative real. So yes, you're 180 degrees one way or from that real side, or from the positive side of the real. If you have a polar zero at the origin, if you have a 0, you're going to have plus 90 degrees, and if you have a pole, it's minus 90 degrees. You're then going to label each frequency range 1 decade before to 1 decade after that frequency. This range is where you're going to have an effect from that polar zero. So again, it's not additive like the magnitude, it's only within that certain range. So for a 0, you add the slope only during that range 1 decade before to 1 decade after. For a pole, you're going to have a negative 45 degree slope per decade. For an example, if your location is omega 10, meaning that you have a polar zero, if it's a pole, we're going to do the example of a pole at 10, you have a range from 1, which is 1 decade before, divide by 10 for the decade before, and multiply by 10 for the decade after. If it's at 10, divide by 10 gives you 1. If it's at 10 and you multiply by 10, you get 100. So your range is from 1 to 100. And the effect during that range is that minus 45 degree slope per decade. Okay, so for the phase, you're going to mark all these ranges. And then if you have ranges that overlap anywhere, you're going to add the effects during this particular points where they overlap. Anywhere else, there's no effect and it returns to 0 slope as long as there's no affecting range. So let's look at an example. So we're going to use now this straight line approximation to draw the Bode plots just from the equation itself. So this equation came from a derivation and analysis for an actual circuit that had inductors and capacitors in them. So it created this transfer function. Again, this transfer function is the output over the input. And then it was created to be in this form. So the first step is that we want to get the standard form. So the standard form is where we have to have any S quantity have plus 1. So in order to do that, we take this 100, and if we take the 100 out, we have to divide by 100 for that S. And notice that this quantity, 100 times S plus over 100 plus 1, is the same as this quantity, S plus 100. So you have to make sure they're the same. So the next one, we're going to have to take out 1K, and that means we have to divide by 1K and then plus 1. And on the bottom, we'll have to take out this 10 in order to get the form of the +1 there. And we're going to take out this 10k to give s over 10k plus 1. So now all these numbers out in front, 100, 1k, 10, and 10k. And then the quantities, so the next step is I like to write them from the lowest value up to the highest value. So those are going to be my poles and zeros. So those are the location underneath the S. So the 101k are going to be zeros. And the 10 and 10k are going to be poles. And again, I order them from the lowest to the highest. So 10 is going to be a pole, and that is going to be the lowest value. 100 is next, and that is a 0. And then 1k is also a 0. And then we have a 10k. So these are our poles and zeros. So now I want to draw the magnitude, and remember that the magnitude, you're going to take, if you have no poles and zeros at the origin, you're going to take this number that's here and multiply it by 20 log base 10 of that number to get the starting value for your magnitude plot. And it is going to be in dB. So 20 log of this number gives me 0 dB. So that is going to be my starting value. And so that is in dB. So my graph has dB as the y-axis. And I'm going to start it at 0 dB. I'm going to label a value here of 0 dB. And I'm going to call the first point here as 10, which means this is then going to be 100, 1,000, and then 10,000, and so on. So omega, which is in radians per second, and then this is going to be a 1 starting value. So I'm going to mark this point here as minus 20 dB, and I'm going to have this flat value until I reach the first point of 10. So at 10, I have a pole, which means that it changes it by minus 20 dB per decade. So I'm going to circle all of my poles and zeros. So I have a 10, 1k, and 10k. Each of these worked out to be exactly on the decade. So at each one of these, I'm going to have a different change, and I'm going to add that to the slope of what I had. So to begin with, I had 0 slope. I got to 10. I add on a minus 20 dB per decade. So that's going to give me this change. And so at 100, I have 20 dB per decade. Then I'm going to have another change at 100, which is a plus 20 dB per decade. So I add that to the slope, which was minus 20 dB, and then I add this plus 20 dB per decade, and that equals 0. So I don't have any slope here until I reach 1k, where I add on to that 0 another 20 dB per decade. And so between 1K and 10K, I'm going to go back up to that 0 dB, because 1 decade I get a change of 20 dB. This is 1 decade. And then at 10K, I'm going to have the change again of a negative 20 dB per decade. So I add those together from minus 20 to plus 20. That becomes a 0 slope again. So that will now continue on at 0 at the value of 0 dB. And that completes the graph for my magnitude plot. So for phase is going to be in degrees. And again, we have 10, 1, 100, and then 1,000. And this position, again, remember, is the location where right after it is the largest gap. And so we first need to find our starting slope. So we go back to our standard form equation, and there's no poles or zeros at the origin, and we have no negative for that coefficient out in front. So we have a 0 degree starting slope, and now we want to mark each region. So remember, this does not add like the magnitude. This is totally separate. You have to identify each region. So we knew that we had a pole at 10 and a pole at 10K, and then we had zeros at 100 and 1,000. So for each one, there's going to be a range 1 decade before to 1 decade after. So I'm going to mark that. For this 10, divided by 10 is 1, multiplied by 10 is 100. That range is going to have the effect of the pole, which is a minus 45 degree slope per decade. That means that over 2 decades, I'm going to get a minus 90 degree change. So at 10K, I'm going to have a 10K divided by 10 is going to give me 1,000. 10K multiplied by 10 gives me 100,000. So this range, I also have a minus 45 degree slope per decade. And then I do the same for each 0. So for 100, the change is from 10 to 1,000. And that change is the 0, which is a plus 45 degree slope per decade. And 1 decade before 1,000, divide 1,000 by 10 gives me 100. Multiply 1,000 by 10 gives me 10,000. That range also has a plus 45 degree slope per decade. So anywhere that these ranges have an overlap, I need to add the effect. So between here and here, I have 0 degrees because minus 45 plus 45 give me 0. Between here and here, I have plus 45 plus 45, so I get a plus 90 degree slope per decade change. And then from here to here, again, I have an effective 0 degrees of change. So I'm going to start this off. I'm going to just find a range in the middle and call that 0. So I'm going to label this as my 0 degrees. Make sure you label the y-axis. And then I have a minus 45 degree slope until I reach 10. So I'm going to go down to minus 45. And between here and here, I have a change of minus 45. From here to here, I have 0 change, and then I have 90 from here to here. So I'm going to go to 45 here. And this is now going to change from that 100 to 1,000. I change by 90. So from minus 45 plus 90 gives me plus 45. Again, I have a 0 change from here to here. And then I also have a minus 45 from here to here. So this is my 0 again, and then it's going to be 0 degrees change after that, and it's going to end at 0 degrees. So this was 0 degrees. So this concludes the solution for this equation for both the Bode plot, or for the Bode plots, both a magnitude plot and a phase plot. And the phase plot is there. Thank you for watching.